Greetings to all of you. Let us study the structure of benzene. So, it is just not the study of structure of benzene, it is considering various concepts and then arriving at the structure of benzene. Now, what is this benzene? All of you must have seen it in your laboratories. It is a colorless liquid, flammable liquid of course, and it has sweet smell and its molecular formula is C6H6. Now, where is it available? What is the source of benzene? This is a constituent of crude oil, and how it is important to us? It is an important component of gasoline. We will be using it as a fuel, and in some cases it is used as a solvent as well in the laboratories. Now, what is the structure of benzene? Is it a straight chain compound having multiple bonds? Let us see that. Now, if it is a straight chain compound which is having a multiple bond, that means it is an unsaturated compound. So, all such unsaturated compounds, they decolorize bromine in carbon tetrachloride. So, bromine has got a reddish orange color. So, when we add this few drops of this to benzene, let us see whether it can decolorize that color. 1 or 2 drops of it, shake it properly, the color remains, and we will take another unsaturated compound hexene, add few drops of it and then shake it, and we see that the color is decolorized. And we can take one more example, that is a dilute solution of KMnO4, add a few drops of it to benzene, 1 or 2 drops, and then shake it. The color remains, color of KMnO4, purple color of KMnO4. And whereas in case of hexene, which is an unsaturated straight chain compound, in that case the color of KMnO4 is discharged. So, that means benzene is not having a straight chain structure. What are the other possibilities? The other possibility could be it can have a cyclic structure. So, what is the cyclic structure? So, it will be having let us see the bromination of this to confirm its cyclic structure. The benzene is taken, bromine is added to that, and then some amount of ferric bromide is added. When this compound is heated, you will get a compound of this color, yellow color. So, only one compound is produced, that is bromobenzene. Now, that means all the 6 hydrogens are identical in this case. This is possible only with a cyclic structure. How do we get that cyclic structure? Something like this, and this structure is informed by some scientist's dream of a snake eating its own tail. So, if it is a cyclic structure, it could be like this, the possibility could be like this, and there are various other possibilities. Which one is true? To confirm that, we have to study hybridization and bonding in benzene. Let us do that. When we do that, so carbon in benzene is sp2 hybridized. All of you have studied this in your previous classes. Carbon undergoes sp, sp2 and sp3 hybridization. So, when it undergoes sp2 hybridization, one s orbital and 2 out of 3 p orbitals, they combine to form 3 new orbitals, and they look something like this. So, the shape of sp2 orbitals is like this. Now, there is one p orbital which is left unhybridized with each of these carbon atoms, which is something like this. Now, the 6 carbon atoms, they form a bond like this. So, they form sigma bonds with the neighboring carbon atoms, which are also sp2 hybridized, and there is one sp2 hybrid orbital is left with each of these carbons, and they will form a bond with hydrogen. Now, which is the other orbital that is left with each carbon atom? That is a p orbital, am I right, which is present in a plane perpendicular to this. Now, all these 6 carbon atoms, since they are sp2 hybridized, they form a planar structure, and they play bonding, all the bonds are present in one plane, whereas the unhybridized p orbital which is present here, that is in a plane perpendicular to those 6 carbon atoms. So, which looks something like this. Now, each of these p orbitals are also having 1 electron each, am I right, and they can overlap sidewise. So, when they overlap sidewise, so they can form single and double bonds, but that is not the case in benzene. In benzene, all the 6 bonds are identical. So, therefore, it is just not simply sidewise overlapping with the neighboring p orbitals. Now, all these p orbitals, they are going to overlap in such a way that the pi electrons, they get delocalized over 6 carbon atoms like this. So, that means there is a plane in which all the 6 carbons and 6 hydrogens are present, and above and below this plane these pi electrons are distributed, electron density is distributed, which looks something like this or something like this. Now, this delocalization of 6 pi electrons definitely gives some special stability to benzene, but that is not the only factor which is involved there. So, which is the other one? To study that, we need to consider the linear combination of atomic orbitals. What is the meaning of that? Probably you have studied molecular orbital theory. So, atomic orbitals, they combine to form molecular orbitals, am I right? Similarly, here the p unhybridized orbitals which are present in a plane perpendicular to that, they also can overlap or combine linearly to form new orbitals which are called as molecular orbitals. So, in this case the combination happens like this. So, this one combination of this p orbitals forms a molecular orbital, second one and the third one, this is the fourth one, next one is the fifth one, and this is the sixth one. Now, if we compare the energy of uncombined p orbitals with the combined p orbitals, we see that there are 3 orbitals which are having lower energy than the corresponding atomic orbitals and 3 having higher energy. The ones which have got lower energy, they are called as bonding molecular orbitals, and the ones which have got higher energy, they are called as antibonding molecular orbitals. Now, these are the specifications of these orbitals, molecular orbitals. Psi 1 is the one which has got lowest energy, psi 2, psi 3 have got same energy, slightly higher than the psi 1, and those two have got same energy, therefore, they are called as degenerate set of orbitals. Similarly, psi 4, psi 5 antibonding orbitals, they are also degenerate, and psi 6 has the highest energy antibonding molecular orbital. Now, in case of benzene, how many electrons we need to fill? We need to fill 6 electrons, isn't it? So, those 6 electrons, they will be occupying all these bonding molecular orbitals which have got lower energy. So, because these lower energy orbitals are completely filled, that gives a stability, special stability to benzene, which we call it as aromaticity. This stability is just like ideal gases which have got completely filled shells. So, the special stability of benzene is due to the presence of 4n plus 2 electrons, and this stability is extra stability, we call it as aromaticity. Now, the question comes, where is this 4n plus 2 coming from? Now, the 2 will be from this orbital, the 2 which is common for all aromatic compounds, and the 4n electrons that comes from this 4 set of 4 electrons, and how many such sets are there which gives 4n plus 2. So, in case of benzene, there is only one set. So, n is equal to 1. So, therefore, there are 6 pi electrons. So, to summarize this, benzene is aromatic because benzene molecule is cyclic, the molecule is planar, the molecule has got complete conjugation of pi electrons within the system or within the ring. In addition to that, it has got 4n plus 2 pi electrons, where n is equal to 1 in this case. Hope you enjoyed understanding the structure of benzene and aromaticity, that is the special stability of benzene. Thank you.